So with this video, we will be starting off with the graph series, and the first video in this series will be Introduction to Graph, where we will be learning about what different kinds of graphs we have and all the conventions. So with this video, we will be starting off with the graph series, and the first video in this series will be Introduction to Graph, where we will be learning about what different kinds of graphs we have and all the conventions. So with this video, we will be starting off with the graph series, and the first video in this series will be Introduction to Graph, where we will be learning about what different kinds of graphs we have and all the conventions. So with this video, we will be starting off with the graph series, and the first video in this series will be Introduction to Graph, where conventions that revolve around the graph that will be used going forward. We will be learning about conventions that revolve around the graph that will be used going forward in the next. We'll be starting off with the graph series, and the first video in this series will be Introduction to Graph, where we will be learning about what different kinds of graphs we have and all the conventions that revolve around the graph that will be used going forward in the next set of videos. So you see this structure, okay? Now this structure is generally known as a graph. Now let's talk about the types of graph. Now this structure is known as an undirected graph. Why? I will tell you. Whereas this structure is known as a directed graph. You would have guessed why, because you see arrows over here, that is why directed. You don't see arrows over here, that's why undirected. But what are these things? We need to know that as well, right? So let's understand. So in graphs, you will see these circular things, okay? And those are generally known as nodes. Remember this, nodes or vertex. We generally call them as nodes or vertex. Now these nodes are represented by a number. Like for an example, I said this is the node 1, this is node 2, this can be node 3, this can be 4, this can be 5. There is no specific order in which you number the nodes. The numbering of the nodes can be in any order. Remember this. So over here, how many nodes we have? We have exactly 5 nodes. So we write the number of nodes as 5. Remember this, the number of nodes as 5. We can also call this as V, which is the number of vertex. Now every node, like if you see this, 2 nodes are connected, right? These 2 nodes are connected by a horizontal line. Now what is this horizontal line referred as? This horizontal line is referred as an edge. So if I be specific, this edge can also be known as or called as undirected edge. Why undirected edge? If you see, the edge can also go from 1 to 4, right? Or the edge can also go from 4 to 1. So it can be a bi-directional edge. The edge can be in both the directions. So thereby, whenever you see an undirected graph and there is a mention that there is an edge between u and v, it resembles that there is an edge between u and v, as well as there is an edge between v and u. So an undirected graph means there can be an edge in both the directions. So as of now, we just need to know about these terminologies: node, vertex, undirected edge, and this is known as an undirected graph. Okay, now is it compulsory that the graph has to be something like a circle or something like that? We will be talking about that, but before that, let's understand what is a directed graph. The only difference in a directed graph is this thing that you see over here. This will be a directed edge. Remember this thing will be a directed edge. Rest everything will stay the same. Imagine if I number this 1 and 4, then I can only say that there is an edge between 1 and 4, which means if I'm standing at 1, I can go to 4, but if I'm standing at 4, I cannot come back to 1. So this is what we call as directed graph. A directed graph is a graph where all the edges, please mind this word, where all the edges are directed. Where all the edges are directed. Can there be multiple directed edges? Yes, you can also have something like this where you say there is an edge between 1 to 4, there is an edge between 4 to 1. So you can also have bi-directional edges as well. So that is the two kind of graphs that we generally have. One is the undirected graph, while the other one is the directed graph. So that was about the types of graph. Now let's understand the other type of graph. Now there are something known as cycles in a graph. Remember this, cycles in a graph. Now you might be thinking, what does graph mean? Is it always a circular structure or what it is? Now I can say, if I just draw some graphs, this is also a graph. We don't see a circle. Yes, we don't see a circle getting completed. We can say this is also a graph. Now you might have read in the binary trees. If you have not read binary trees, you can definitely read them from my playlist. So this is a binary tree, but this can also be called as a graph. Why? Because it follows all the rules. We have nodes, we have edges, and they're perfect. And that is what is the minimal condition for anything to be called a graph. So this guy can also be called a graph. So a graph does not necessarily means that it has to be an enclosed structure. It can be an open structure as well. Okay, so this is where something as cycle comes in. Okay, now what is a cycle? Cycle definitely means if you're starting from a node, you reach back to that node. Remember this, start from a node and end at that node. That is the definition of a cycle. Now if you carefully observe over here, can I say this has a cycle? Yes. Why? Because if you start from 1, you can go to 2, you can go to 5, you can go to 4, you can come back. So there is a cycle in this graph. There are multiple cycles. You can also say this is a cycle. You can also say this is a cycle. So there can be multiple cycles. So if there is a single cycle in a graph, you generally call that as an undirected cyclic graph. Undirected cyclic graph. The definition graph does not assume that it is an enclosed structure, but the moment you attach the term cyclic to it, we can always call it as an undirected cyclic graph. I hope that is sure. Now, let's come back to this example and let's omit this. Now, this is a directed graph. Do we see a cycle over here? Now, this, no. Do we see a cycle here? No. Do we see a cycle here? No. So this directed graph does not have a cycle because we are starting at 1. But we are not ending at 1, or we are starting at this particular node, but we are not ending over here. So unless and until we start from a node and we end at there via some path, I'll tell you what path is, we don't call that as a cyclic graph. So we can call this as directed, like acyclic graph. So it's generally known as acyclic graph. Acyclic means no cycle. So directed acyclic graph is what we call this. Okay, but over here, if I just attach a edge, if I just include another edge, we can say that this graph has a cycle. Why? Because yeah, this is a cycle. So it will now become directed cyclic graph. But without this edge, it is known as directed acyclic graph, which is commonly known as DAG, which you will be hearing in the next set of the lectures. Fine. So let's come to the next term, which is path. Now, what is the definition of a path? Can contain a lot of vertices, contain a lot of nodes or vertices, and each of them are reachable. Very important. Each of them are reachable. Okay. So what does this mean? So assume I write something like 1, 2, 3, 4, 5. So we know that this is a graph. Again, satisfies all the definition. You have nodes, you have edges. So this is definitely a graph, right? So over here, what we see is, if I write 1, 2, 3, 5, it is a path because 1, 2, 3, 5. This is a path because you go from 1 to 2 to 3 to 5. This is a path. But if I write something like 1, 2, 3, 2, 1, this is not a path. Why? Because you're saying 1, 2, 3, and again you're saying 2. You cannot have a node appearing twice in a path. A node cannot appear twice in a path. Remember this. A node cannot appear twice in a path. It can only appear once. Is this a path? No. Why? Because you say 1, you say 3, you say 5. But how do you reach from 1 to 3? There is no connectivity from 1 to 3. There is no edge from 1 to 3. So you cannot. So a path that you're writing, the adjacent nodes must have an edge between them. Like 1, 2 has an edge, 2 and 3 has an edge, 3 and 5 has an edge, so that you can travel in that path. So that is what is the definition of a path. So the next term, you reach from 1 to 3, there is no connectivity from 1 to 3, there is no edge from 1 to 3, so you cannot. So a path that you're writing, the adjacent nodes must have an edge between them. Like 1, 2 has an edge, 2 and 3 has an edge, 3 and 5 has an edge, so that you can travel in that path. So that is what is the definition of a path. So the next term that we will be learning is the degrees in a graph. So assume if I name them as 1, 2, 3, 4, 5, and I say, can you tell me the degree of the node 3? So remember, the definition of a degree is the number of edges that go inside that or go outside that total. So I can say there is 1, 2, 3, which is attached to 3. So the degree of 3 is 3. Similarly, the degree of 4 is 2. Why? Because there are 2 edges which are attached to it. The degree of 5 will be 3. The degree of 2 will be 2. And the degree of 1 will be 2. So the definition of a degree for an undirected graph, very important, for an undirected graph is the number of edges that are attached to it is known as the degree of the graph. And there is a property as well. Please take care of this property. The property states that the total degree, yes, the total degree of a graph is equal to twice of the number of edges, is equal to twice of the number of edges. Why? Because every edge is associated to two nodes. That is the reason. Why? Because every edge is associated with two nodes. So let's compute the degree. So the degree of this is 2, again 2, 3, 2, and 3. So if I compute the total, we will be getting 6, 3, 9, 12. So the total degree of this graph is 12. And if I compute the number of edges, 1, 2, 3, 4, 5, 6, 6 number of edges, and the property gets satisfied. Intuition is very simple. Every edge is connected to two nodes, thereby this particular property stands. So this was for undirected graph. Now let's talk about something which is directed graph. Now remember this, in directed graph we have two different things. One is the in degree of a particular node, while the other one is the out degree of this particular node. Now what do you mean by in degree or out degree? So imagine this is the graph. Okay, so let's quickly draw a graph. And perfect. So if I ask you for this particular node, okay, ask you for this particular node, what is the in degree for this node? What will be the answer? Assume this node is node number 3, is the in degree, so that's 2. So if I ask degree is 1, so the in degree and out degree will be in this way. So that will be in terms, that's very important to understand what is an edge weight. Now we talk that, okay, these are nodes and this is an edge. Now every edge will be having a weight. Now in problems that you'll be facing, they might say that this edge has a weight 3, this edge might have a weight 2, this might have 1, this might have 5, this might have 6, this might have 2, this might have 1, this might have 5, this might have 7. They can assign any weights to any edges, and this is what we call as edge weight. What if weights are not assigned, like they don't tell you what are the weights? In that case, we will always assume unit weights, which is 1. If the weights are not assigned, we assume unit weights, that is 1. So guys, that will be it for this particular video. I hope you understood everything that I taught in this particular video. Just in case you did, please hit that like button. So in the previous video, you did learn about graph and its types. You must be thinking, which is the complex data structure that we will be using to store graph in our programs. Now, in this video, we will be learning about how to represent a graph in C++. In the next, it's going to be Java. Okay. So imagine this is the particular graph that is given to you. Now, there will be two portions. Obviously, someone will give you the input. So first portion is the input, and next will be how do you store it. Okay. So first, let's understand the input of a graph, and then we can think about how to store in a data structure. So in all the questions, what they will tell you is given n and m. Okay, they'll always tell you given n and m. And in the starting of the question, they'll tell you if the graph is a directed one or if the graph is an undirected one. If the line states given a graph, given an undirected graph which contains n nodes and m edges. So n will be given to you. So n nodes and m edges. So the first thing that you will definitely do is you'll take the input of n and m, right? So over here, what is the number of nodes? The number of nodes over here is 5. The number of edges is 6. 1 edge, 2 edge, 3 edge, 4 edge, 5 edge, 6 edge. The number of edges is 6. The number of edges is 5. So in the input, 5 and 6 will be given to you. Just 5 and 6. You have to assume the first one is node and the next one is the number of edges. Now, if they're saying you edges, In order to represent a graph, you have to understand the edges are between which nodes. Now in the next line, they will be giving you M lines. Remember this. M lines that will represent edges. M lines that is going to represent edges. So for an example, if there is an edge between 1 and 2, the input might tell you 1, 2, or the input might tell you 2, 1. It can be either way. If they tell you 1, 2, we assume that there is an edge between 1 and 2, and there is also an edge between 2 and 1, right? So obviously 2, 1 means 1, 2, and 1, 2 means 2, 1, vice versa. I can say that there is an edge between 1 and 3. I can say there's an edge between 2 and 4. I can say there's an edge between 3 and 4, 2 and 5, and 4 and 5. So I have written all the 6 edges. Do they follow a specific order? No, they can be given in any order. So this is the next set of input. So the input will be containing like this: 2, 1, 1, 3, 2, 4, 3, 4, 2, 5, 4, 5, right? So this is how the input will be. So you have to assume the first line, this is N, this is M. The next set of lines, M lines, are the number of edges. Is there any specific boundary on the number of edges? Is it somewhere related to the number of nodes? No. If I draw one more edge, it becomes 7. If I draw one more edge, it becomes more. If I draw one more edge, it becomes more. If I draw one more edge, it becomes more. They can be, like, M can be anything. N will be constant, but M can be anything. Okay. So this is how we take input. Like, this is how the input will be given. Now the question comes, how do we store? So there are two ways to store. One is the matrix way, and the second one is the list way. Okay. So first let's learn about the matrix way. So the first way is to use a matrix, and we generally call that as an adjacency matrix, the way that we use. So assume that this is the graph, okay, and these are the edges that are given to you. You need to store these edges somewhere. Either you can store these edges, or these edges has to be stored somewhere so that the future algorithms can be performed. So where will you store these edges? This is where something like a matrix comes in. Okay, first thing that you'll observe is the number of nodes were 5. Are the nodes 0 based or 1 based? And we see the nodes are 1 based. If the number of nodes are 5, the last node is n equal to 5. So it is 1 based indexing nodes. Okay, so what you will do is you will define an adjacency matrix of n plus 1 and n plus 1 size, which is this, and it will have the indexes 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. Okay, now if they tell you that there is an edge between 1 and 2, what you do is you go to 1 and you go to 2 and you take the intersection, yes, and you mark it as 1. And did I tell you, if there is an edge between 1 and 2, it means there is an edge between 2 and 1. So you go to 2, you go to 1, and the intersection as 1. Perfect. Next, there's an edge between 1 and 3. So 1 and 3 is marked as 1, and 3 and 1 is marked as 1. Next, you go to 2 and 4. 2 and 4 is marked as 1. 4 and 2 is marked as 1. Next, you go to 3 and 4. 3 and 4 is marked as 1. 4 and 3 is marked as 1. So in this way, you can mark all these edges like 3 and 5, 5 and 3. Next, 4 and 5, 5 and 4. So all these edges are marked as in the adjacency matrix. Now all the remaining guys will be filled on with zeros. You can, or you can just leave them. All the remaining guys will be filled on with zeros. So this matrix will tell you, if you want to check if there's an edge between 3 and 4, yes there is. If there's an edge between 4 and 2, yes there is. Is there an edge between 5 and 2? No, there is no edge. So this matrix is going to tell you if there is an edge between a particular node to another node, and how much space are you using. Remember this, the space that you'll be using will be n cross at n, because you're using almost like n plus 1 into n plus 1, which is equivalent to n into n space, is what you will be using. And this is a costly thing. Yes, this is a costly thing. But if we're moving on to the next thing, which is cheaper, let's check out the code super quick. So what did I say? The first line will contain n and m. So define n and m and take it as input. Done. Now if it is something like 1 based indexing graph, you take like this. If it's a 0 base, then you take a n cross m, and that will work. Now what is the next lines containing? It was containing m lines. So you just run a loop for m lines, and you know, for every line they will be giving you that there's an edge between u and v. So you take them as input. What did I say? Have the intersection marked as 1 and have the reverse intersection marked as 1 as well. So both them. So in this way, I can say the entire graph has been stored here, right? And what will be the time complexity? This is big O of n that you took to store the graph. After that, we can perform the algorithms, but at first it's very important to understand how to store a graph. So in the previous method, we saw that it was taking n square space. This is where something like how to store a graph. So in the previous method, we saw that it was taking n square space. This is where something like adjacency list comes in, and it takes n squares. At first, it's very important to understand how to store a graph. So the graph. After that, we can it was takes very less amount of space. Now, what is an adjacency list? We use an array. Yes, we use an array. But the array that we will be using, like over here, we see that the size is 5, right? And we're using an one based graph, one based indexing graph. So what we will do is we will create an array of n plus 1 size, which is 6 size, and it will be like 0, 1, 2, 3, 4, and 5. So you have created an array of 6 size. Now this array will contain list, and in C++ the list is nothing but vector of int. Yes, in C++ it is nothing but vector of int. So we can call this array as adjacency list. So a list of adjacency containing this. So apparently what happens is every index is containing an empty vector. Every index is containing an empty vector. You could have defined integer, then it would have contained an integer. You could have defined double as well. The moment you define something as vector, it containing an empty vector. Every index is containing an empty vector. You could have defined integer, then it would have contained an integer. You could have defined double as well. The moment you define something as vector, it means it contains an empty list or an empty vector. Done. So as of now, we have 6 indexes with empty vectors. So you need to remember one thing. What is the motive of the list? So if you see 4 has 2, 5, 3 as its neighbor. So the motive of the adjacency list is on 4, I just want to store 2, 5, 3 in any order. So that if someone tells me who are the adjacent neighbors of 4, I can say 4 is connected to 2, 4 is connected to 5, 4 is connected to 3. That is my motive. Okay. So on the first step, we have something like 1 and 2. So what we will do is we will go to 1 and we will say the list, can you take 2? Because if 1 and 2 are connected, 2 is definitely a neighbor of 1. And similarly, can I say 2, please store 1? Perfect, because for 2, 1 is also a neighbor. For 1 and 3, can I say 1, can you store 3? And for 3, can I say, can you store 1? Yes. For 3 and 4, can I say 3, can you store 4? And can I say 4, can you store 3? Yes. For 2 and 4, can I say 2, can you store 4? And can I say 4, can you store 2? Yes. For 2 and 5, can I say 2, can you store 5? 5, can you store 2? For 4 and 5, can I say 4, can you store 5? 5, can you store 4? I can. So this will be the end of the day list. And if you carefully observe, 1 has its neighbor as 2 and 3. 5 has its neighbor as 2 and 4. 3 has its neighbor as 1 and 4. So you stored all the neighbors in particular indexes. This is how the list works, right? And if you carefully observe, the number of edges were 1, 2, 3, 4, 5, 6. How much space did you take? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because the space that you take is twice of edges. Why? Because every edge has 2 nodes. So for every edge, you're storing twice. So you'll take bgo of 2a, 2e is the space that you will take in storing this particular adjacency list, which is much better than your n square, because in n square a lot of places were unused. Over here we are storing who matters, no one else. So the input of n and m will be same. what we do is we declare an adjacency, and all the once you an adjacency, can you please store v, because v is a neighbor on the list, and the space complexity will be much lesser. Now let's come back to what if it's a directed graph. If you remember, if it's a directed graph, we mean there's an edge between u and v only. So if there is an edge between u and v, will we require this line? Obviously not. This line will not be required. If there is an edge between u and v, the edge only goes from u and v. So v will only be the neighbor of u. It won't be the neighbor of the other one, right? So that is what we do. And in case of directed graphs, the space complexity used will be big O of E. Why? Because we are not consuming two edge complexity used will be big O of E. Why? Because we are not consuming two edges. We're just consuming one edge. So thereby we can easily say the number of edges will be the space complexity used in a directed graph. And going forward, we will be using adjacency list in every problem, not adjacency matrix, because of the space complexity issues. So as of now, you've understood how to store an undirected graph, a directed graph. But what if I ask you, how do you store a weighted graph? What does a weighted graph means? Now, what if the graph comes up something like, okay, there's an edge between 1 and 2 and the weight is 2. There's an edge between 1 and 3, the weight is 3. Edge between 3 and 4, the weight is 4. Edge between 2 and 4, the weight is 1. Edge between this has 6. And then edge between this has 3. What if they start assigning something like weights to it? Yes. What if they start assigning edge weights? That's when you call that as weighted graph. So the first technique that we learned was matrix, right? And if there is an edge between 1 and 2, you basically went to 1, went to 2, and you wrote 1 in it. So instead of writing 1, you take the edge weight 2 and you write in both the places. So that's a slight change that you have to do. You have to go back to the code, and instead of saying equal to 1, you say equal to weight. So it's going to be like adjacency of u, v equal to weight, right? But that was of matrix. But if I ask you, how do you store in a list? So if you remember, in the list, we were doing something like 0, 1, 2, 3, 4, 5. And for 4, the neighbors were 2, 3, 5. If you carefully observe, for 4, the neighbors were 2, 3, 5. So how do you store the weights? So as of now, you're just storing 2, 3, 5. So instead of that, what you'll do is you'll store pairs in it. And you'll say 4 can be like, okay, I know it has 2, but it has 2, 1 because the edge weight is 1. I know it has 3, but it has 3, 4 because the edge weight is 4. I know it has 5, but the edge weight is 3. So instead of storing something like 2, 3, 5 as single guys, you will just tweak the data structure to store pairs, and those pairs will be like, the first guy will be the 4 to 2, and the second guy will be the edge weight. The first guy will be 4 to 3, and the second guy will be the edge weight. So while defining the list, instead of integer, you have to define a pair class of integer and integer, and you can easily store the weights as well. I'll be showing you the implementation probably in some video where we will be solving a problem in weighted graphs. But as of now, just keep this in mind. So I hope you have understood the entire implementation of Graph. Just in case you did, please make sure. So in this video, we will be learning about connected components in a graph. Now, what do we mean by connected components? Till now, we have seen graphs like this, if you remember well enough. We've also seen graphs like this. In the first lecture, I told you this is also a graph. It might be a binary tree, but this can also be called as a graph. This is a connected graph, so we can also call this as a graph. But what if I ask you, is this a graph? Like if I show you something like this, is this a graph? Then you might say, yes, Trevor, this is a graph, this is a graph, this is a graph, this is a graph. There are 4 graphs. This is a single node. This can also be treated as a single node. You're correct. You're absolutely correct. These are 4 graphs. But can I say these 4 graphs, can they be one single graph? You might say, no, Striver, they're not connected. This is where the definition connected components come in. So if I try to number them, for an example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so number them. Imagine someone comes up and says the definition of graph. Given an undirected graph with 10 nodes, 1, 2, 3, 4, 5, 6, 7, 8, 8 edges. And he says the edges to be 1, 2, 1, 3, 2, 4, 3, 4. Okay, 5, 6, 6, 7, 5, 7, and 8, 9. He just tells you about these 8 edges. So apparently, it's a graph. It's a graph which is in 4 pieces. It's a graph which is in 1 piece, 2 piece, 3 piece, 4 piece. The last one being a single guy. So this is what we call components. Instead of piece, it's 4 components. The graph has been broken down into 4 different components. So next time you see 2 different portions and they're not connected, don't say that those are not graphs. So these are 4 different components of a single graph. Yeah, they could have been 4 different graphs, but according to the question and the input, you can say them to be a part of a single graph. So you will be applying a lot of algorithms going forward. Okay, applying a lot of algorithms. You'll be learning about algorithms. Assume a traversal algorithm. Okay, assume a traversal algorithm. I'll not take any name because I haven't taught you that. So what will happen in future is, if assume you're doing a traversal algorithm, you'll be like 1, 2, 4, 5. Assume you started a journey and you start like 1, then you go to 2, then you go to 4, then you go to 3. So on this traversal, you will never be able to reach these components. You will never be able to reach these components. This is why any traversal that you will do, any traversal, you will always use something as a visited array. Yes, you will always use something as a visited array. Remember the concept visited array. Over here we have 10 nodes. So what you'll do is you'll create an array of 11 size starting from the 0th index, and you can go on till the 10th index. So the size of the array will be 11. And what you will do is, remember this, you will always run a loop for any algorithm from 0, and this node numbering is from 1 to 10. So you can always run a loop from 1 to 10, always. And if the node is not visited, remember this, if the node is not visited, you will call the traversal algorithm from that node. I'll explain you now what happens. You might be confused what is happening, but let's understand. So initially what you'll do is you'll say everyone to be unvisited, which is false. Okay, everyone initially is unvisited, so thereby it will be false. So what happens is, when you start your traversal from 1 and you see 1 is unvisited, so you see 1 is unvisited, yes, the if says 1 is unvisited, so you go and say traversal of 1, traversal of 1. So 1 starts a traversal, and the traversal algorithms are designed in such a way that they will traverse the entire connected portions of the graph, entire connected portions of the graph. So it goes to 1, goes to 2, goes to 4, and goes to 3. So apparently it will mark, because it went to everyone, right? It went to everyone. So it will mark everyone as visited because it traversed everyone. Now the traversal, I will move to 2. So it will see 2 is already visited. In my traversal, yes, in my traversal, I have already visited 1, 2, 3, 4. So I'll not go for 2, then I'll go to 3, I'll not go, then I'll go to 4, I will not go. Next, when I go to 5, I see 5 over here is 0, non-visited. Then you again call the traversal for 5. Now 5 will traverse, 6 will traverse, 7 will traverse. So it's done. Next you'll be like 6, 7. Next it goes to 8. 8 will say I have not been visited. So now you'll go and do a traversal for 8 and 9, and you'll mark it as true. Next, 9 traverse. Next you go to 10, not traverse, so 10 will be visited. So in this way, any algorithm in the future, you don't just call, like, you can't do something like, okay, we start the traversal algorithm from node 1, and this will make sure that it visits everyone. This is not possible if the graph has multiple components, because you carefully saw, if you started from 1, you would have only visited this portion, and these portions would have not been touched. So for any traversal algorithm, just make sure this is the pattern. This is the pattern. You always run from 1 to 10, and you check for 1, not visited. Go and start it. So it will mark everyone whom he can. For the next guy, again he goes. For the next guy, again he goes. For the next guy, again he goes. So this is how the traversal algorithms will be executed, and this is what the connected components are. Okay, so guys, I hope you have understood this video. Just in case you did, please make sure you like this video, and if you're new to our channel, what are you waiting for? Hit that subscribe button right away, man. Just hit it. So in order to solve any graph problems, we have to know traversal techniques. And the first traversal technique that we are going to learn is BFS traversal technique. Now, what is BFS? It is nothing but the breadth first search technique. Okay, you must have heard about this if you have read trees. So this is the first technique that we are going to learn. And in the next video, we will be learning something as DFS. We'll talk about DFS in the next video, but as of now, let's focus on BFS. In order to solve any problem, you have to know the traversal technique. So you cannot skip this video. So what is BFS? As the name suggests, so this is the first technique that we are going to learn, and in the next video we will be learning something as DFS. We'll talk about DFS in the next video, but as of now, let's focus on BFS. In order to solve any problem, you have to know the traversal technique, so you cannot skip this video. So what is BFS? As the name suggests, breadth, very important term, breadth first search. Now usually graphs are of two kinds. One can be the one based indexing graph, which is this one. If you carefully see, n is 8 over here, and the graph numbering starts, like the node numbering starts from 1. Or it can be 0 based indexing, where the graph numbering starts from 0. That is okay, you just need to make sure you write the code according to that, but the logic remains same. So let's come back to BFS. So what is breadth first search? So this term is very important, breadth. It kind of signifies level wise traversal as well. This is also called as level wise traversal, but yeah, generally the generic term is breadth first. So let's understand. So usually they will be telling you a starting node. Okay, so assume I say you over here the starting node is 1. So I'm saying that this is the starting node. Okay, now what we say is, okay, this is at the level 0. That is what we generally say. This is at level 0, and then you say these guys are at a distance of 1. So you'll call them as level 1. Then you say these guys are at level 2, and then you say this guy is at level 3. So what you do is, in breadth first search traversal, first you visit the first guy, that is the starting node, and you write that. So that is something that you have written. Then you go to all the guys that are on the next level. So this was at the 0th level, so the next level will be nothing but first. So I can say this is at the first level and this is at the first level. Now in the breadth first search traversal, you can either traverse this and then this, or you can either traverse 2 and then 6. That is completely your choice. So I will decide to travel 2 6. You can travel 6 2 as well. That is completely okay. So this is also done. Now the next level is level 2, and you know these all guys are level 2, correct? So what you do is you say, okay, again you can write 3 4 7 8. You can write something like 8 7 4 3. That is completely your choice, as long as you are traversing all the nodes in the level wise fashion, we are completely okay with it. So it is like 3 4 7 8. So see, this is level 0, this is level 1, and all of these are level 2. So the level 2 can be traversed in any of the ways, but they should be traveled together. Okay, next will be level 3, and this is level 3. So I can say this is level 3. So this will be the breadth first BFS traversal of this particular graph. But if the starting node is 1, very very important, if the starting node is 1, what if I change the starting node? So let's quickly change the starting node and understand the particular graph. But if the starting node is 1, very very important, if the starting node is 1, what if I change the starting node? So let's quickly change the starting node and understand BFS in depth. So assume I tell you that the starting node as of now is 6. Okay, so I've changed the starting node. Remember this? This is the starting node and this is at level 0. If this is at level 0, you cannot say this to be at level 0. No, this only one node can be at level 0. So you write 6 at level 0. Now if I ask you which is at level 1, then what you do is you say this is at a distance 1, this is at a distance 1, this is at a distance 1. So all of these guys are at equivalent distance. Very, very important. All of these guys are at equivalent distance. So thereby you call them as level 1, level 1, and level 1. Again, you can travel 1 first, then 7, then 8. That is your choice. So I'll decide to travel 1, 7, 8. So this is level 0. This is level 1. You need to understand the distance, breadth. It goes equivalent in the breadth. So it was here. It went equivalent in the breadth. That is very important to understand. Okay. Next, if I ask you the next level, that's 2. So for this is level 2. This is level 2. And are there anyone else who is level 2? I don't see. So I can say, okay, this guy is level 2 and this particular guy is level 2. So you can again write something like 2 and 5. So this is level 2. Perfect. And it's time for level 3. So obviously 1, 2, 3. So this will be 3. Similarly 1, 2, 3. This will be 3. And are there any other? No. So this is 3. This is 3. So there are 2 guys who are 3. So it's very important you travel breadth-wise, and everything depends on the starting node. Depending on the starting node, the traversal will change and you will always travel in the breadth-wise manner. I hope that is clear. In order to do a BFS traversal, there is an initial configuration that you need to start off with. So whatever is the starting node given to you, what you do is you clearly take a queue data structure. Now, if you don't know queue data structure, please read about that. You take a queue data structure. Queue is nothing but first in, first out. The guy who goes in first gets out first. So the initial configuration says, I'm going to define a queue data structure and that will always contain this particular guy. Remember this, that will always contain this particular guy starting node. And there is another thing that you need to do. You need to create something as a visited array. Okay. And this visited array is something which is very common in all the graph questions. And over here, if you see the node is numbered till 9. And since the graph is 1 based, what you'll do is you'll create this visited of a size 10. Okay, please make sure you create of a size 10. So this is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this will be the visited one. And whatever is the starting node, you go over there and you mark it as 1. And everyone else will be marked as 0. So over here, please understand this. 1 means this guy is already in the queue. Whenever I say someone has been traversed, someone has been touched, wait, mark that as visited. So this will be the initial configuration initially a queue which contains a starting node, initially a visited array which will be of size depending on its 1 based or 0 based, you can decide, and the starting node will be traversed, so thereby it will be marked as 1. This is going to be the initial or the starting configuration in a BFS traversal. What is the next step that you'll do? Whatever is in the queue, you will start taking it out, start taking it out, start taking it out till the queue is not empty. Remember this, keep taking out till the queue is not empty. Okay, so whatever is at the queue data structure, I take it out and you'll print it. So assume I print this. So this is printed, right? This is printed as a BFS traversal. Now, very important, whatever you take out of the queue, one you took out of the queue. So if you remember this graph, you would have stored this in some data structure. And which data structure was that? That data structure was adjacency list. Do you remember? Yes. So what will be the adjacency list for this particular graph? Can I say for 0, it will be an empty data structure. For 1, it will be storing this 2 and 6. Remember this? Okay, let's write for the next. For 3, it will just be storing 2. So please write that. Sorry, for 2, you have to write in the next step. For 2, it will be storing 1, 3, and 4. So let's write 1, 3, and 4. Next will be for 3. Let's check out for 3. For 3, it's just storing 2. So let's store 2 in it. Next will be 4. For 4, it is having 5 and 2. So for 4, it will be 2 and 5. For 5, for 6, for 7, for 8. Similarly, create the entire adjacency list that I have already taught you in the second video. So kindly create this, and after that we can start off with the BFS traversal. So how the what you do is you go to 1 and you say, who are your neighbors? I repeat, you ask, who are your graph? You can see that. So if you remember, this guy stores all the neighbors. What you do is you take 2, you take 6. First take 2, put that into the queue data structure, okay, and mark it as 1. Next take 6, put it into the queue data structure and mark it as 1. Perfect, done. So first iteration of 1 is done. So it is very perfect, done. So first iteration of 1 is done. So it is very simple. Let me repeat. You took out 1, you basically went to its neighbors and you put that into the queue and marked it as visited. Next time, take out the next guy. So I'll take out the next guy 2. Do the same thing on this 2 as well. Go to 2's neighbors. Who are 2's neighbors? How will you know? Again, 2's neighbors are 1, 3, 4. Very obvious. 1, 3, 4 are its neighbors, and that is stored in the adjacency list. So 2's neighbors were 1. But remember this, 1 will not be put into the queue. Why? Because you've already traversed 1. Because you've already traversed 1. How will you know that? Because yes, 1 is already marked as visited. So you already know 1 has been touched or traversed. So you'll not take 1. Instead of that, what you'll do is you will simply omit 1 and you'll not put that into the queue. Let's check out the next. It is 3 and 4. So you'll just take 3 and you'll take 4 and put that into the queue and mark 3 and 4 as visited. Perfect. This is done. Next, you take the next element out, 6. So 6 is there. Again, do the same thing for 6. Who are 6th neighbor? 1, already visited. 7, not visited. 9, not visited. So you take 7 and you take 9 and you put that into the queue data structure. At the same time, mark 7 as true, 9 as true. Perfect. Done. 6 is done. What is the next thing? 3. Let's take out 3. Who are 3's neighbors? Just 2, already visited. Nothing to do. So 3 is also done. Let's take the next one out. 4. Who are 4's neighbor? 2, already visited. 5, take 5, put that into the queue, mark 5 as true. Perfect. 4 is also done. Next, take 7. Who are 7's neighbors? 6, visited. 8, not visited. Take 8 and put that into the queue and mark it as visited. Perfect. Next, so 9. What about 9? For 9, there's one neighbor 6, but that is already visited. So done. Next, take 5. For 5, who's the neighbor? 4 and 8. And if you carefully see, 4 and 8 are already visited. So no need to do anything. 5 is also done. Next, take 8. And for 8, if you see 5 and 7 are already visited. No need to do anything. So this is also done. Apparently, if you see, this is your BFS traversal. Yes, this is your BFS traversal. 0th level, 1st level, 2nd level, and the 3rd level if you carefully see. So we were successfully able to print the BFS traversal of a particular graph, right? Now it's time that we check out the code. So I hope you've understood the entire explanation. Now it's time to check out the C++ code and the Java code. So what I'll do is I'll write the C++ code and I'll explain every step. And the Java code is on the left so that you can just follow for every corresponding C++ step what will be the Java code, and we are going to follow the same structure of code, so you'll not face a problem. So generally what will happen is you'll be given something like vector int, where you have to store the BFS and return, and always you'll be given the number of nodes, and you will be given the adjacency list. You don't need to create the adjacency list. They'll be giving you the adjacency list in almost all the problems. Now this problem states a directed graph, but we will be coding this for an undirected graph, and then I'll tell you why the same code will work for directed graph as well. Okay. For an undirected graph, and then I'll tell you why the same code will work for directed graph as well. Okay, so what is the initial step if you remember? So first let's quickly check if this is a zero-based indexing graph. So if you see, it is a zero-based indexing graph because the graph is starting from 0, right? So what you will do is you will just create an int visited array of n size and probably mark everything as this. And you know the initial configuration will be having 0, and we will have a queue. Okay, it is a zero-based indexing graph because the graph is starting from 0, right? So what you will do is you will just create an int visited array of n size and probably mark everything as this. And you know the initial configuration will be having 0, and we will have a queue. Okay, and in the queue, you know it will be having the starting node. Done. Now what we did, we always took out everything from the queue till there was something in the queue. So can I say always take out, like, till it is having something, till it is having something, till the size is like still is not empty, just take it out. And I can say the node that is taken out, like it will be q dot front, and we can just say q dot pop. So this will make sure you always get the node. And can I say if I have to store the VFS, I can just do it over here, and I can easily store whichever node comes out. That is what gets into the BFS. Done. What is the next thing that we did? We always took out the node if you remember, and we checked out its neighbor nodes, right? So who is storing the neighbor nodes? Yes, the adjacency list. So for this node, can I say if I do auto of IT of adjacency node, what does this mean? Whenever I write adjacency node, I'm saying index node. That adjacency element will be a vector. It's the adjacency list. So for this node, can I say if I do auto of IT of adjacency node, what does this mean? Whenever I write adjacency node, I'm saying index node. That adjacency element will be a vector. If you remember the vector adjacency list, if you remember the list, if you say index, that index is storing a vector, and that vector is storing all the neighbor elements. So you have to just iterate on them. So these are the neighbor elements, IT. You just need to check, have they been previously visited? If not, you say, okay, let me visit them. Very simple. And let me put them into the queue as well, so that in the next step, they can be taken into the BFS. Once this is done, you can say this is my answer. Once this is done, you can always say this is my answer. Okay, now let's quickly compile this and check. So if you see the compilation is successful, and let's quickly now submit the code and check if it's working fine. And then, so it's time to understand the space complexity and the time complexity. Space complexity is very simple. the compilation, again do the same thing for 6. Who was 6th neighbor? One already visited, 7 not visited, 9 was also, and storing. Need to check, have they been previously visited? If you can say this, quickly compile this and check. So if you see the compilation is successful, and let's quickly now submit the code and check if it's working fine. And then, so it's time to understand the space complexity and the time complexity. Space complexity is very simple. A queue, a visited node, and a BFS list. So bgo of 3n, which is almost equivalent to bgo of n, and the adjacency list is given to you, so you can just omit this. And what about the time list? So bgo of 3n, which is almost equivalent to bgo of n, and the adjacency list is given to you, so you can just omit this. And what about the time complexity? The time complexity is very simple. Now, if I go and analyze the time complexity, I know one thing for sure. If you look at the code, in the code, this is running. And you know, every time a node will come and go into the BFS. So a node goes once into the BFS. I know for sure. Goes once into the BFS, right? So if a node goes once into the BFS and it runs on all its neighbors, can I say it runs on all its degrees? Runs on all degrees. So can all its degrees, and it runs on all its neighbors. Can I say it runs on all its degrees? Runs on all degrees. So can I say it's something like while q not empty, and then there's a for loop, and this for loop runs for all node, and it will run for the number of degrees of that node, because if this guy has 3 neighbors, it's going to run for 3 neighbors, all degrees. So can I say this for loop is what it is running? So thereby I can say the time complexity to be the queue itself will run bgo of n times, because there are n nodes, and this inside guy will run for total degrees. And if you remember the total degrees, we have already concluded as twice of edges. This was done in the first lecture. The total degrees, because for every node we traverse all the neighboring nodes. So this will be these nodes. You can say the time complexity to be the queue itself will run bgo of n times, because there are n nodes, and this inside guy will run for total degrees. And if you remember the total degrees, we have already concluded as twice of edges. This was done in the first lecture. The total degrees, because for every node we traverse all the neighboring nodes. So this will be the time complexity for this particular guy. So guys, I hope you've understood the entire BFS algorithm. Just in case you did, please make sure you like this video. And if you're new to our channel, what are you waiting for? Man, just hit that subscribe button right away. And with this, I will be wrapping up this video. If you haven't checked out our DPCs and the SG sheet, the links are in the description. Make sure you check it out. With this, let's wrap up this video. Let's meet in some other video. Till then, bye-bye. Take care.
Whenever your heart is broken,
So in this video, we are going to learn about the second traversal technique, that is the DFS traversal in a graph. Now, in the previous video, you did learn about something which was BFS, breadth first search, which was based on level. Now we will be learning as DFS, which is depth first search. Now this will be based on depth, depth, depth. Yes. So why did I emphasize so much on depth? You'll understand. Again, similarly, you'll be given a graph and you'll be given a starting node. Assume the starting node to be 1 over here. Okay. The starting node is 1. This is 1. Okay. Now you go to any one of the neighboring nodes, 2, 3, 4, anyone you can go. So for example, I decide I will go from 1 to the left neighboring node, which is 2. So if you go to 2, you don't stop there. Very important. You started from here, you go here, and then you don't stop. You go depth, depth. So you go to depth, which is 5. Again, you can either go to here or here. That is your choice. But generally, we go to the guy who is right at the first of the adjacency list, or from left to right. So 5 will be there. So you basically go like this. So it's like 1, 2, 5. Done. Now you've gone like 1, 2, 5. There is no further depth in it. So what you do is you come back, and now you go to here, which is the adjacency list, or from left to right. So 5 will be there. So you basically go like this. So it's like 1, 2, 5. Done. Now you've gone like 1, 2, 5. There is no further depth in it. So what you do is you come back and now you go to here, which is the 6, which is the 6. So you go to 6, right? Now you went like 1, 2, 5. You came back, you went to 6. Now there is no depth of 6. So you come back. Now there is no further children of 2. So you go back. Now once this portion depth is completed, now it starts going to the next portion, which is 3. So you go to 3. Done. Now when you've gone to 3, now again, either you can go this way or you can go this way. That is your choice. So I decide I'll go this way. So I'll go like 7. I'll go like 7. Okay. So I go 7. Now you're like 1, 3, 7. Now 7's depth is 8. Does not needs to be in doubt. No depth of 6. But the depth in 2, 5. Done will be there. So right at the first of the adjacency list or from left to right. So 5 will be there, which is 5. Again, you can either go to here or here. That is your choice. But generally, we go to the guy who is right at the first of the adjacency list or from left to right. So 5 will be there. So you basically go like this. So it's like 1, 2, 5. Done. Now you've gone like 1, 2, 5. There is no further depth in it. So what you do is you come back and now you go to here, which is the 6, which is the 6. So you go to 6, right? Now you went like 1, 2, 5. You came back, you went to 6. Now there is no depth of 6. So you come back. Now there is no further children of 2. So you go back. Now once this portion depth is completed, now it starts going to the next portion, which is 3. So you go to 3. Done. Now when you've gone to 3, now again, either you can go this way or you can go this way. That is your choice. So I decide I'll go this way. So I'll go like 7. I'll go like 7. Okay. So I go 7. Now you're like 1, 3, 7. Now 7's depth is 8. Does not needs to be in doubt. Neighbor. 7's depth is 8. So you go to 8. 8's depth is 4. So you go to 4. So apparently you started from 1. You came to 3. You went to 7. You went to 8. You went to 4. And after that, you can't go because this is already done. So you go back. There is no further. Go back. No further. Go back. No further. Go back. So apparently this portion is done. Had there been someone else, something like 3, 4, 9, 10, then coming back, you'd have gone to 9, 10. So you go to depth. You go to depth at first. I hope that makes sense. So this will be the DFS. This will be the DFS. Again, it's not necessary that you go like this, then this. You could have done the other way, like 1, 3, then you could have gone like this 4, 8, 7, then you could have gone to 2, then to 6, then to 5. You could have done that way. That is, as long as you're traversing in depth, any traversal type will work, but it should be depth. Okay, so let's change the starting node in order to understand the DFS traversal more. Okay, so assume I change the starting node to be somewhere around 3. Now assume this is the starting. So again, this will be the first point for sure. This will be the first point. Now from 3, you can either go here, you can either go here, you can either go here. Your choice. So I decide I'll go to 4. From 3, I decide I'll go to 4. So it'll be like 4. Then you'll go to 8. Then you'll go to 7. So it'll be like 3, 4, 8, 7. So 3, 4, 8, 7. So 3 went to 4, 4 went to 8, 8 went to 7. Cannot go further. Comes back. So this portion depth is completed. Now go the other way, which is 1. So you go to 1. You go to 2. Again do the same thing. 5 and then 6 or the opposite. It's like 1, 2, 5, 6. Now come back again. Now 3, will it go to 7? No, because 7 has already been covered. So if you start from 3 and you go in this, then you go in this, this will be the DFS. There can be plenty of DFS depending on the starting node. Yes, depending on the starting node. And which algorithm, if I ask you, which algorithm usually goes to the depth, solves it, comes back? Yes, you said that correctly, recursion. That is absolutely correct. The algorithm that always goes in depth, like if you remember, this kind of algorithm is, do you remember? This kind of algorithm is nothing but recursion. And if you have not seen the recursion playlist, I will highly recommend you go back and watch my recursion playlist, at least till video 7, at least from video 1 to video 7, because entire graph without recursion will be nightmare. You need to understand how graph works in DFS traversal, otherwise it will be a big mess. So again, for this graph, where do you store that? You store this graph in an adjacency list. That is something which you will do. So please go and store this graph in an adjacency list. So this is how the adjacency list for this particular graph will look like. Now, assuming the starting node is given as 1, okay, assume the starting node is 1, what will be the initial configuration? Again, similar to BFS traversal, you will first create a BFS. So first create a visited array. Again, please go and check if it is a 1-based indexing. So if you see a 1-based 1 to 8, so please create like a 9 size array, 0, 1, 2, 3, 4, 5, 6, 7, 8. So a visited array is what initially you will start off with, and whatever is the starting node, just mark it as visited, and everything else will be staying as 0, similar to what we did in BFS. Done. What will be the next step? Remember this. The next step is going to be whatever is your starting node, you call a recursive function. Remember this. You call a recursive DFS function from that. Okay. Now what you will do is this DFS of 1. I'll write the code somewhere. DFS of node. What this will do is the moment it gets into the function, it states, hey dude, listen, this guy is done, and this is a part of my DFS. Well, you can just add a list, and you can say this is a part of my DFS. Okay, so this is the line where you will do the DFS traversal because you're visiting a node, so stored. Now what you do is, remember this, what you do is you went to 1. Now either you can go to 2, either you can go to 3. You go this depth or you go this depth. So you travel the neighbors. Either you travel 2 first or 3 first, that is your headache, but you travel the neighbors at first. So how do you travel the neighbors of 1? Very simple. They're stored in the adjacency list. If you carefully see, they're stored in the adjacency list. So for any node, you go to their adjacency list, right? So this is nothing but adjacency of 1. So this is the vector, this is the list. So that is what you'll pick up. So pick up the list and run a for each loop in it. So these are the neighbors. Run a for each loop in it. Adjacency of node. So this is the list of neighbors, and you're running it. And now you go depth by each node. So first you go to the depth of 2, then you go to the depth of 3. So first go to the depth of 1 IT, which is 1 neighbor, and in the next iteration, the next IT will go. So imagine this to have 2, 3. What will happen? First a call of 2 will be made. So it will be like DFS of 2 is made. Then when this completes, the call completes because it is a recursive call. It's a recursive call. When it completes, then it goes to DFS of 3. You need to understand this. Okay. So it's basically something like, okay, let's get back. It is something like, okay, first we have 2. So let's call the DFS for 2. It will go and it will complete, like go to the depth, and then come back. Then the next guy will be 3. Then it will go to DFS of 3 and then come back. So it's like DFS of 2 will be performed in depth, then DFS of 3. But you don't visit every time all the nodes, because when you go to 2, it will have the neighboring as 1, 5, 6. But from 2, you will not go back to 1. From 2, you will not go back to 1. So it's very important. A node which has been visited in its traversal, you don't visit it again. So what you do is, you say, okay, listen, this node has to be unvisited for me to go into the depth of it. This node has to be unvisited for me to go into the depth of it. Simple. So this will be the simple lines of code that you need to execute. So what will happen is, DFS of 1 will come and will mark it as visited. Now it has 2 neighbors, 2 and 3. So it will go to the depth of them, right? So for 2, it again goes and checks there is 1, but that is already visited. Then there is 5, and then there is 6. So it will go for both DFS for 5 and then DFS for 6. So how is the call coming up? First the call was for 1, right? So you can write 1. Next the call went to 2, right? Next the call went for 5. So now for 5, when you go to 5, remember this by the way, when you go to 2, you'll mark it as 1. Now you go to 5, mark it as 1. Now for 5, what happens is, see here, for 5, the neighbor is 2, which is already marked. There will be no further calls. So 5 will say there are no further calls. There are no neighbors, so I don't call anyone. So I will come back. I came back, right? Now DFS of 2 goes to DFS of 6. 6 says, do I have neighbors? I do 2, which is already visited. No further calls. Comes back. Now 2 says, do I have any other neighbors apart from 5 and 6? No. I go back. 1. So 2 is completed. So initially when you started with 2, it is completed. Now the next guy 3 will be occurring. Next guy 3 will be occurring. So you go to 3 now. 3 is marked as visited, and now you're traversing 3. So the next, we go to DFS of 3. So let's check out who are the neighbors of 3. So the neighbor of 3 appears to be 4 and 7. So first we will go to 4, then we'll go to 7. But apparently what will happen is, when you go to 4, 4 in turn will go to 8, 8 will go in turn to 7. So 4, when it goes to depth, it will visit 7. So thereby this call was made. Depending on where 4 lies on the adjacency list, we made this call. If there was something like 7, 4, you would have gone like this. So it depends on the adjacency list, which format, like which traversal you will traverse. Okay, so for 3, who are the neighbors? 1, no. 4 and 7. 4 and 7. First we go to 4. Perfect. Let's go to 4. Then we will think, shall we go to 7 or not? Then we will think, shall we go to 7 or not? We are not sure as of now. But DFS of 4 is sure. Let's go to 4. Market is visited and 4 is there. Perfect. Now let's go to 4. Who are 4's neighbor? There should be 3 and 8. 3 is already visited, but 8 is not. So let's go to 8. Very simple. Again, if you're going to 8, market is visited. At the moment you go to 8, who are 8's neighbors? 4. No need to go. 7. Okay, interesting. Let's go to 7. And 7 is visited. Now, who are 7's neighbor? 3 and 8. Those guys are already visited. You have already traversed them. So you do not go. You do not go. Yes, you do not go. So apparently 7 is done. 7 says, I don't have anything. My recursion is done. Can you just go back? He's like, okay, let's go back. 8 says, I don't have any neighbors. Can you please go back? He says, okay. 4 says, I don't have any neighbors. Can you please go back? Yes. So this 3 went into one of its neighbor 4. Will it go to the next neighbor 7? No, because 7 was visited by this path. There is no need to again go and visit 7. So this supposed neighbor is no more visited. Thereby, the DFS is this portion. This is your DFS call. So if you carefully observed from here, whether you went like this or whether you went like this, was dependent on the adjacency list. So I hope you've understood the technique. Now it's time to check out the code. So as usual in the code, so the C++ code is what I'll be typing, and on the left you can see the entire Java code in the similar format. So you can just follow the Java code and you can understand every line while I type the C++ code. The syntax is almost identical. So what do we have? We have the number of nodes and the adjacency list. You don't need to create the graph because that is always given to you. So if you carefully observe, it's a connected undirected graph, and it says the starting index is 0th vertex. So syntax is almost identical. So what do we have? We have the number of nodes and the adjacency list. You don't need to create the graph because that is always given to you. So if you carefully observe, it's a connected undirected graph, and it says the starting index is 0th vertex. So something to observe. It's unique. Now it's time to check out the code. So as usual in the code, so the C++ code is what I'll be typing, and on the left you can see the entire Java code in the similar format. So you can just follow the Java code and you can understand every line while I type the C++ code. The syntax is almost identical. So what do we have? We have the number of nodes and the adjacency list. You don't need to create the graph because that is always given to you. So if you carefully observe, it's a connected undirected graph, and it says the starting index is 0th vertex. So something to observe. It's a 0-based indexing graph. So this will do, right? Perfect. So starting index is 0. So you can say the start is 0. And you need to store so you can create a list in order to store the DFS ls. Okay. So over here you can go back and say cool private, and right here what you can write is void DFS So starting index is 0. So you can say the start is 0. And you need to store the, so you can create a list in order to store the DFS ls. Okay. So over here you can go back and say cool private, and right here what you can write is void DFS. This will be the node, correct? You need this particular adjacency list, so please carry the adjacency list as well. And what is the next thing that you need? You need the visited, so please carry the visited. And you need the list which stores the particular DFS, so please carry the list as well. Now what will you do when you enter? So the moment you enter, you remember this is mandatory, and you add it in the, you add the node into the vector or the list. What's the next step? The next step that you do is you traverse for all its neighbors. So this is how you traverse for all its neighbors. Remember this is the way in which you traverse all its neighbors. Okay. So now what is the first thing that you do? If this neighbor is non-visited, very, very important. If this neighbor is non-visited, you call DFS IT adjacency visit and just pass on the parameters. And this is how the DFS will be. And over here, what you do is you call the DFS the starting node. The starting node can be anything. Pass on the adjacency, pass on the visited, pass on the ls. Once the entire DFS has been completed, you return the ls. And now you can just go and compile. Hopefully it runs. So if you see visited of n, okay, as usual, our common mistake. This will be B. If you see the output is correct, let's quickly submit this. So internally, the code has also been written in such a way that it follows the adjacency list. So you don't need to worry. The code will be working fine. So this is what is the DFS traversal of a graph. So let's talk about the space complexity. So what will be the space complexity? How many nodes are we visiting? At max, we are visiting n nodes in our traversal. So we can say that we are storing n nodes in those DFS traversal. We're using bgo of n for visited, and the recursion stack space at the worst case, because what is stack space? If you remember recursion, this is the stack space. So the worst case, if I give you a graph like a skewed graph, you will end up going like 1, 2, 3, 4. So the recursion stack space at the worst case can be bgo of n. So I can call it near about bgo of n if you do not include the adjacency list. What about the DFS traversal? So how's the DFS traversal? It's a function, and then it iterates on the neighbors, right? Iterates on the neighbors. And for every neighbor, it calls the function. This is how it is, right? So this function will always be called for a single node. This function, graph like a skewed graph, you will end up going like 1, 2, 3, 4. So the recursion stack space at the worst case can be bgo of n. So I can call it near about bgo of n if you do not include the adjacency list. What about the DFS traversal? So how's the DFS traversal? It's a function, and then it iterates on the neighbors, right? Iterates on the neighbors. And for every neighbor, it calls the function. This is how it is, right? So this function will always be called for a single node. This function will always be called for a single node, right? And any node, for any node, it will just be called once, because you traverse a node single time. For node 1, it will come once. For node 2, it will come once. And for every node, we will have a certain number of neighbors that it is iterating. It is iterating. So can I say for an undirected graph? Can I say for an undirected graph, these neighbors for 3, the neighbors are 1, 7, and 4, which is the degree of the graph. Which is the degree of the graph? Can I say it is the degree of the graph? Like, sorry, degree of 3. Yes. And for every node, can I say it will be the summation of degrees? So can I say it will be the summation of neighbors or the summation of degrees? I can say summation of degrees, because for every node, it will be the number of neighbors plus number of neighbors plus number of neighbors, which is equivalent to degree of a node plus degree of a node plus degree of a node, which is equivalent to summation of degree, right? So what is the summation of degree? If you remember the first lecture, that is 2 into number of edges. And then for every node, you're calling the function once. So bgo of n for calling the recursion once. So this is the time complexity for an undirected graph. For a directed graph, it will depend on the number of edges. So this 2 will go off, and the number of edges is what it will boil down to. So guys, I hope you have understood the entire explanation as well as the code and the time complexity and the space complexity. Just in case you did, please hit that like button. And if you're new to our channel, what are you waiting
square to value. Okay, so that's it. The range is over here. Good. Range is over here. Okay, so we know the upper limit and lower limit are the same. So last thing I'm gonna tell you is we can put these two pictures, all of these point back to this point, this problem. So we can think this point. This point is moving. I know that. Okay, now if you move here, fall right. Good. X plus 2. I can't really think about it. I can't really draw to you really good, but you can imagine this
waiting for. Hit that Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, we are going to solve this particular problem, number of provinces. What does the problem state? The problem states you're given an undirected graph with V vertices. We say two vertices U and V belong to a single province. If there is a path from U to V or from V to U, your task is to find the number of provinces. So let me explain you the question. So imagine a graph is given, which is something like this. Like this is a particular piece, and then there is something like this. Then imagine there is something like this. Okay, so what they're saying is this is an entire graph that is given to you. Now, what they're calling a province is, if you see, if you take this province, you can go from 1 to 2, you can go from 1 to 3 as well. From 3 to 2, you can go, from 3 to 1, you can go. From 2, you can go to 1, from 2, you can go to 3. So, from every other node in this province, you can go to every other node. Thereby, this is a province. And if I take this, this is also a province because 4, 5, 6, every one of them can go to each other. Similarly, 7, 8 is a province because everyone, like 7 can go to 8 and 8 can go to 7. Now, I cannot call this as a province because if you wish to go from 2 to 4, you will not be able to go because there is no connectivity. So, thereby, this is first, tell me the rate this or how do you calculate the number? It's very simple. Now, you have read about the BFS traversal and the DFS traversal. You've read about both the traversals in the previous lectures. You can use any one of them because you know if you use any one of the traversals, it visits all the nodes in a graph. The BFS will visit everyone level wise, and the DFS will visit everyone in the deep. Right? That is something which you know. Now I can use any of that algorithm. You can use BFS or you can use DFS. So imagine if I say, okay, there is a starting node or the node that you start the DFS traversal is from 1. I'm talking about DFS. So what will happen is you'll start from 1, you will go to 2, you will go to 3. So apparently you end up visiting 1, 2, and 3, but you'll not be able to visit this nor this. So can I say if I call the, yes, can I say if I call the traversal 3 times, once from 1, once from 4, once from 7. Can I say if I call the DFS traversal once from 1 DFS traversals, starting from 3 different starting nodes, and thereby I can get 3 provinces, right? We know how to do a DFS traversal. We have learned about that. But in that case, there was a single starting node. Over here, the starting node can be multiple. So we can see if somehow we can figure out the starting points, then we will be able to figure out 3 provinces. But now you might have a question in your mind, does the starting point needs to be 1? No. Any starting point like 1, 2, 3, it can be anyone. It can be anyone. It can be anyone. If you start from any one of these given points, it will make sure it visits everyone. It will make sure it visits everyone, right? So somewhere down the line, if I can figure out the starting points, my job will be done. This is where what we do is we use something as a visited array. Now we see there are 8 nodes. So we will create a 9 size visited array. 1, 2, 3, 4, 5, 6, 7, 8. So it's like 0, 1, 2, 3, 4, 5, 6, 7, 8. Perfect. We have created a 9 size visited array and we mark everyone as false. And this is known as the visited array. Done. Now what we do is we say, okay, listen, for int I equal to 1, because we know the numbering of nodes start from this to v or n, and we say, hey, listen, if visited of I is equal to 0, or that means it has not been visited, can you call the DFS from this node? This is what we write. This can be BFS as well. Yes, this can be BFS of I as well. You know both the algorithms. You can write either of them. So now what happens is, for the first time, I is 1. Okay, it goes and checks if it's visited, and it finds that it's not visited. Thereby it says, okay, I'll consider 1 as a starting point, and I'll call the DFS for 1. I'll call the DFS for 1. Now, I'm not going to teach you DFS because you know that. If you don't know that, go back to the previous video. So if you do the DFS of 1, what will happen is 1 will be visited, 2 will be visited, 3 will be visited in that DFS call, because a DFS algorithm makes sure that you visit all the nodes in a graph. So it will make sure that it visits, right? And then the call will be over. The call came from DFS 1, it will go to DFS 2, it will go to DFS 3, and then it will come back, then it will come back, and then it will come back. Now in the process, when it goes from 1, it marks 1 as visited, if you remember. Then it marks 2 as visited, then it marks 3 as visited, and then it goes back ultimately. So the DFS call makes sure that 1 is marked, 2 is marked, and 3 is marked in the visited array, right? The next time what happens? The I becomes 2, and it goes and checks, is that visited? Yes. Next time, visit. So apparently comes back. Now we make it 5, and you see that 5 is already visited. Then we make it 6, already visited, then we make it 7, not visited. So this time the DFS call goes for 7. Now when the call goes for 7, the starting node is again assumed to be 7, marks 7 as visited. That is one of the ways that you can do it. Or what you can do is you can use this adjacency matrix and solve this particular problem. Now what I will do is, since we have been doing everything in adjacency list, what I'll do is I'll just quickly create our adjacency list, assume to be 7, marks 7 as visited, goes and does the call for 8, marks it as visited, goes back and goes back. So this is how we can say the visited array performs, and this after this term will be 8 and it will not find it, then it will be 9 and the for loop will be over. So can I say this particular if statement was apparently into sort of adjacency matrix? Okay, so one of the ways is either you create your adjacency list and then just go across. That is one of the ways that you can do it. Or what you can do is you can use this adjacency matrix and solve this particular problem. Now what I will do is, since we have been doing everything in adjacency list, what I'll do is I'll just quickly create our adjacency list. So it's very simple. You just do it something like this, and you're given the adjacency matrix. So you can just run a couple of loops, something like this, and you can say, hey, listen, if adjacency of I and j is equal to 1, that means there is a node. And please make sure you don't have self nodes. Like I should not be equal to j, which is basically the self node. So this is the adjacency list. What I can say is adjacency list of I can say of dot push back of j, and similarly we can say adjacency list of j dot push back of I. Once you've done this, your adjacency list is ready. Now we know that what do we need? We need a visited matrix. So we can just take a visited matrix and you can mark it as 0. What is the next thing that you'll do? You will go from 0 to v, by the way, not n, I plus plus, and you will say if it is not visited, can you go and call the DFS with this particular starting node and this adjacency list and the visited array. And at the end of the day, you need to count the provinces. So you can do is int count equal to 0, and you can plug in a counter plus plus for loop that runs, and then there is a DFS call, right? So you might think, yes, we can created an adjacency list. Let's not take that into account because in most of the problems, adjacency list will be given to you. So let's not discuss about the adjacency list. Apart from that, we're using a visited array which takes bgo of n, a skewed graph space complex that runs, and then there is a DFS call, right? So you might see that bgo of n into the DFS we know takes v plus 2e. So, but this is wrong. It's not this. Instead of that, it is n plus v plus 2e. Why? Let's go back. And then there is a DFS call. How much time does it take? So you can argue that Striver, there is a for loop that runs, and then there is a DFS call, right? So you might see that bgo of n into the DFS we know takes v plus 2e. So, but this 2e. Why? Let's go back. So how many times is this DFS executed? 3 times for this particular graph. Once for here, once for here, once for here. And whenever it's executed for one, a DFS call for this is made, a DFS call for this is made, a DFS call for this is made. So in total, 3 DFS calls are made. Whenever it is executed for 4, in total, 3 DFS calls is made. Whenever it is executed for 7, in total, 2 DFS calls is made. So overall, can I say I'm making a DFS call for all the n nodes? I'm making a DFS call for all the n nodes. Can I say that? I can. So thereby, I can say this is the outer loop, and the inner loop overall throughout the loop journey runs for the DFS times for the entire graph. It runs throughout because partially it will run for when the starting node is 1, then the starting node is 4, then the starting node is 7. So partial DFS, partial DFS, partial DFS sums up to overall DFS of the graph, and the overall DFS of the graph is having a complexity of near about v plus 2e, near about v plus 2e, and this can be like equivalently said as near about a linear stuff. Near about, again, it's not exactly because v plus 2e is there, then depends on the number of neighbor nodes as well. Imagine you get a graph as like 1 2 3 4 all single nodes, then there will be no neighbor nodes for any one of them, so it will boil down to bgo of n. as well. Imagine you get a graph as like 1, 2, 3, 4, all single nodes. Then there will be no neighbor nodes for any one of them. So it will boil down to big of n, a single DFS, which has no neighbor nodes. So big of 1, a single DFS, big of 1, single DFS, big of 1, and no neighbor nodes. So big of n for the for loop, and big of 5 calls. So big of n again. So depending on the neighbor nodes, the time complexity will vary. So overall, we can write that as a big of n traversal. So guys, I hope I was able to explain you the time complexity and this particular method, because trust me, you're going to see this a lot in the next set of the questions that we are going to do. So I hope you understood it. So just in case you did, please hit that like button. And if you're new to our channel, what are you waiting for? So we have learned about the BFS traversal and the DFS traversal, but where will it be applied? So you're going to do a bunch of problems, and this video is going to be about the first problem, number of connected components. So let me explain you the problem. So what does the problem state? The problem states you'll be given a grid of size n cross m, where n is the number of rows and m is the number of columns in the grid. And zeros are meaning water, and 1 is meaning the land. Okay, so your task is to find the number of islands, and an island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically. or diagonally in all 8 directions. So basically what they are stating is they'll be giving you a grid of one is meaning the land. Okay, so your task is to find the number of islands, and an island is surrounded by water and is formed by connecting adjacent lands horizontally or vertically or diagonally in all 8 directions. So basically what they are stating is they'll be giving you a grid of size n cross m. Okay, over here 0 means water, 1 means land. Now you have to find the islands. So this is a land, this is a land, this is a land, this is a land, this is a land. So I can say these all lands are connected. These all lands are connected because this can be connected like this, like this guy is connected to 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 this. Or you can take the other way. These guys are connected, these guys are connected, these guys are connected, these guys are connected. They are connected in somehow because all the 8 direction connectivities are allowed. All the 8 direction connectivities are allowed. So I can say these piece of lands are connected. And then there is water, 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 water. And then this piece of land is connected. And this piece of land is connected. So apparently I find 3 pieces of land or 3 pieces of island. First island, second island, third island. So there are 3 islands. So the question states, tell me the number of islands. Tell me the number of islands if I give you a grid. Now you might be thinking, but Shriver, this is a 2D matrix. How can this be a graph problem? This is a graph problem. So try to think it as a node. Try to think this as a node, 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 a node. So all these guys as a node. Okay. So if you think that all of these guys as a node or a vertex, carefully observe. This guy is connected to 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 this. So can I say if I start the traversal, it can be any traversal, BFS, DFS, doesn't matter. If I start a traversal from 1, this will make sure it traverses the nearest one. This will make sure it traverses the nearest one. This will make sure it traverses the nearest one. This will make sure it traverses the nearest one. So if I start from a particular one and I do a certain level of traversal, assuming that the connections are in all the 8 directions, then this one will go and traverse this. This one might go and traverse this. This one might go and traverse this. This one might go and traverse this. They cannot go beyond this because there is 0, 0, 0, 0, 0, 0, 0, 0, 0 all over. They cannot go beyond this. So if you do a traversal starting from this one, this will go